So 3D Gaussian splatting. We maybe most of you guys know what is Gaussian. Gaussian is, we know Gaussian distribution, right? This kind of Gaussian distribution. So Gaussian is parameterized by mean, scale, rotation, opacity, and color. There are 5 features in for each Gaussian. So it basically point cloud, as I said, is based on something similar to point cloud. There are many point cloud, but originally point cloud, it only has position and RGB value. But on 3D Gaussian splatting, each point becomes Gaussian. We are in 3D space, so that is the reason why we call this 3D Gaussian splatting. Each point becomes 3D Gaussian, and Gaussian, so each point has mean, scale, rotation, opacity, and color. So each point, that this is some 3D Gaussian, this is some 3D Gaussian. So there are many 3D Gaussians. So each point becomes 3D Gaussian. And splat, that is from Wikipedia. Splat means the sound of something wet hitting a surface, or of something hitting the surface of a liquid. So let's say we have some 3D Gaussian, like this kind of ellipsoid or sphere shape that we can throw 3D Gaussian to a wall, right? Let's say this is image plane, and then we can throw 3D Gaussian, and there can be splat sound, splat. So that is the reason why we call 3D Gaussian splatting. We throw 3D Gaussian from world coordinate system to image space, and then all the Gaussian are splatted to the image space, and then we combine them to get images. That is the reason why we call this 3D Gaussian splatting. We splat Gaussians. And topology free. So, basically it's based on point cloud, right? So it is not mesh, so topology free. It can, theoretically it can represent anything, and then time efficient, very, very fast, very efficient, over 30 frames per second. Some works over 100 frames per second. Very fast, so that we can finally achieve real-time rendering speed. And photorealistic, as you can see from this image is quite good, right? When this is rendered image from 3D Gaussian splatting. Image quality is quite good, but one limitation is the hard to get explicit surface, because each point cloud becomes 3D Gaussian, so there is no concept of some surface. Mesh has explicit surface, but on 3D Gaussian, it does not have surface. It does not have, connectivity. No connectivity, no triangle. That means there's no surface. Just a set of point, where each point becomes 3D Gaussian. So this is rendered 3D Gaussian splatting, and then this is visualized 3D Gaussian. 3D Gaussian, maybe depending on the scale and rotation, each point, and there can be like three axes, and then if scale also 3D, is 3D, rotation 3D, mean is 3D, this is 1D, and this is 3D, because RGB. So the position of Gaussian 3D, it can floating around any position in this 3D scene. And scale, what is the scale? The size of the 3D Gaussian. So for example, taking an example of this one, let's say this is x-axis, y-axis, and z-axis. Then the scale of x-axis is big for this Gaussian, right? But for some Gaussians, maybe like this. Then z-axis scale is big for this Gaussian. So there can be sphere shape or ellipsoid shape of 3D Gaussian. That's the scale about this one. The size of 3D Gaussian for each axis. And rotation. If we have this kind of sphere, ellipsoid, then we can rotate it, right? We can rotate it to any orientation, right? That is about rotation, 3D rotation. We can rotate 3D Gaussian. And opacity means density. In NERF, we learned density, right? NERF. Outputs RGB, and then density, right? It's same. Opacity means density. And RGB, some works uses spherical harmonics. We are not covering spherical harmonics in this course. You can just, spherical harmonics is just a parameterized RGB color. So you can just consider the spherical harmonic just RGB color. So there are how many? 13 dimension. Each point has 13 dimensional numbers, 13 dimensional vector, right? There's 13 dimensional vector. Mean means, assuming we have point cloud, each point has its location, right? That is about mean, mean of Gaussian. And scale means size of the Gaussian. For point cloud, point cloud does not have scale, right? Point cloud, each point is just a point. It does not have size, but in 3D Gaussian, each point has its size in three axes. So that is about scale, the size of the 3D Gaussian. And rotation means we can rotate 3D Gaussian. Of course, also in point cloud, there is no rotation. Each point is just a sphere, so there is no rotation. But as we have different sizes for each axis, then we can rotate 3D Gaussian, right? So that in 3D Gaussian, we can have rotation as well. Opacity is just a same as the density in nerve, and color, RGB. So these are parameterization of 3D Gaussian, 13-dimensional number. And as you can see, this is just a point cloud, so that it's hard to get explicit surface. Sometimes explicit surface is very useful in many cases, actually. But 3D Gaussian splatting drawback is it is hard to get explicit surface. So as I said, this is parameterization of 3D Gaussian, mean, 3D point. And covariance is the combination of scale and rotation, right? Scale, rotation. And opacity, just density of each Gaussian. And color C, RGB value, or spherical harmonics coefficient. So these are typical parameterization of 3D Gaussian. And how can we get 3D Gaussian? Like similar to nerve. We can reconstruct 3D work from images or videos. Like, let's say we take a video with our mobile phone. Then that becomes the input of 3D Gaussian. Actually, that's all. If we have video from our mobile phone, then we can run structure from motion, right? Structure from motion, video. Structure from motion. It gives us sparse 3D point and camera parameter as well, right? That becomes input of 3D Gaussian splatting. Then free view images. Very similar to multi-view stereo, right? Multi-view stereo also takes output of structure from motion, sparse 3D points and camera parameter, and also video, right? Very similar to multi-view stereo. Of course, 3D Gaussian splatting, we can use multi-view images if it is available, but it is not necessary. If we have video, then we can just use it. So, and it's very practical actually. We can just simply take a video from in any scene, and then we can use 3D Gaussian splatting algorithm to get 3D representation of the 3D scene. We do not need to do camera calibration in advance. It is not necessary. Of course, we can do, then it is good, but camera calibration is not necessary. Nothing is necessary actually. Just taking video, that's all. Then we can reconstruct that video, the 3D Gaussian splatting, using combination of structure from motion and 3D Gaussian splatting. Once we get 3D Gaussian splatting, we can use it in many cases. For example, as I said, we can render from novel viewpoints. Once we optimize 3D Gaussian splatting, then we can render any images from any viewpoint. So that is the one application of 3D Gaussian splatting. Of course, we can novel view. It does not mean any viewpoint. It is not any view, because there can be some 3D regions that the video does not cover, right? There can be some regions that is not included in the video. Then such kind of 3D space might not have any data, might not have any observation. That there might be no Gaussian at that space. But some 3D space that is included in the video, then we can render novel view. And then based on this reconstructed 3D Gaussian splatting, we can do 3D level understanding, like 3D point tracking or 3D video editing. This is the final project, right? Once we get 3D Gaussian splatting, then we can edit something on the 3D space, considering visibility or penetration, collision between objects, right? So once we get 3D Gaussian splatting, we can do, like, there can be many things, but exploration, re-render from low value point, understanding, 3D tracking, 3D video editing can be achieved with the 3D Gaussian splatting. But this kind of point-based rendering actually is not a newly introduced in 3D Gaussian splatting. This kind of point-based graphics, point-based rendering actually is introduced quite long ago. The seminal work is surface splatting, introduced in 2001. Elliptical weighted average, in short EWA. So consider oriented points. I mean, there is a point, right? There's a point, and surface. Surface means basic element of surface. We have volume and voxel. Voxel is a basic unit in volume, right? Surface means surface. Surface. Basic element in surface. Consider oriented point surface as discrete sample of a texture function on a surface. And then a Gaussian reconstruction kernel is used to recover a continuous signal such that we can sample it in screen space. So using this kind of combination of Gaussian and point-based graphics, this kind of point-based rendering is already introduced in quite a long time ago. But the rendering quality or efficiency was not good compared to 3D Gaussian splatting. But this kind of point-based graphics, point-based rendering was already introduced a long time ago. Of course, mesh is the standard, always mesh is standard actually. This is introduced in 2001, but mesh is has been always standard in many industry and academic community. These days, it's trying to shift to 3D Gaussian splatting, but I mean there were many alternative like NERF or 3D Gaussian splatting. NERF was too slow to replace mesh. So of course there are many works that try to make it fast, but NERF was too slow, and the photorealism was not very good compared to mesh. So NERF actually didn't replace mesh, but 3D Gaussian splatting, it somehow can replace mesh in many cases. So, and from this one, we can know that if we have surface in this 3D object, 3D space, and then we can project it to screen space, that means moving camera closer scales the point so that object have no holes. I mean, point-based rendering, point cloud is always sparse, right? This point cloud always sparse, so there can be holes in rendered images, but this kind of EWA makes the point, projected point bigger when camera becomes closer, so that there is no hole in the rendered image. And slanted normals appear as the ellipse, so we can create better edges. Each sample can be processed independently, so that makes rendering quite fast. We can do a parallel computation very easily because each sample can be processed independently. So the powered by parallel computation with GPU, these point-based graphics achieve very fast rendering speed. And here, differentiable surface splatting, introduced in SIGGRAPH 2019, show that this process is end-to-end differentiable. So the 3D Gaussian splatting is actually not totally new thing. It is, heavily inspired and built on top of this line of work. There was point-based graphics, point-based rendering, splatting, and then differentiable pipeline of this kind of point-based splatting was introduced in several years ago. And then 3D Gaussian splatting was on top of this line of this work, and then inspired by this work. And then how can we render? in less summary. We will study detail in the next slide, but let's see how to render, how to get images using 3D Gaussian splatting. So each point has, as I said, each point has 3D mean, 3D scale, 3D rotation, opacity, and color, right? 13-dimensional vector, each point. And then we can project Gaussian to the screen space. Project means, assuming Gaussian is in world coordinate system, we can apply camera extrinsic to convert it to camera coordinate system, and then apply camera intrinsic parameter to project it to image coordinate system. It's just the same as what we learned so far. I mean, we have mean is a position of 3D Gaussian, right? So then we can just simply transform its positions to the camera coordinate system and image coordinate system by applying camera parameters. That is called projection. We can project Gaussian to screen space, so that scale, rotation, opacity, color does not change. They do not change. But the only mean changes from world coordinate system to screen space. And then we can sort projected Gaussian by depth order, because Gaussians close to the camera should be rendered, and then Gaussians far from camera might not be rendered because they can be occluded, right? So we need to sort Gaussians according to depth order. Each mean provide position information, right? So we can, once we convert it to camera coordinate system, then we can get depth value for all the Gaussian, right? And then we can sort Gaussians, we can sort projected Gaussians by depth order. And this is to consider visibility of depth-aware visibility of Gaussian, and then accumulate contribution of Gaussian based on depth order. So we sorted projected Gaussian by depth order, and then we can accumulate contributions of Gaussian based on depth order. As you can see from this figure, this is depth order. This one has lower depths, higher depths. This is camera. This is camera. So that we can accumulate contribution of Gaussian based on depth order. This one might be high contribution. This one might be low contribution, because this green one is occluded by the blue one, right? The red one is occluded by blue one. So contribution of all the 3D Gaussian, blue one might be highest and green one might be lowest. And 3D Gaussian splatting, there can be, in these days, people try to introduce neural network in 3D Gaussian splatting to get some generalizable system, but original 3D Gaussian splatting, it is similar to deep SDF, just for a single scene. Nerve, deep SDF, 3D Gaussian splatting, only for a single scene. Once Gaussian is optimized, once Gaussian is optimized for this scene, then the optimized 3D Gaussian splatting can provide images of only this scene. It cannot be used for other scenes. And there is no neural network inside of 3D Gaussian splatting. Of course, we can introduce neural network in 3D Gaussian splatting if you need them, but the original one, it is purely based on optimization without neural networks. And we will cover details later, but it looks very similar, right? We shoot array. This one also, we shoot array, and then we sort all the point or Gaussian based on their depth values, and then we accumulate contributions along the ray direction, right? And then we get final color. Actually, that is based on rendering equation. We learned that nerve is based on rendering equation, right? Rendering equation, not a specific equation for nerve. Rendering equation is governing equation in computer graphics. It tells us how can we get images in general situation, not a specific equation for nerve. Rendering equation is governing equation in computer graphics, and both nerve and 3D Gaussian splatting are based on rendering equation. So that is the reason why they look similar. Cast array and consider density or opacity of each point, and then we accumulate contribution of Gaussian or point based on depth order, then it becomes final color. For the nerve, we do ray marching. We do keep ray marching because we need to evaluate all the points along the ray. But Gaussians, we do not have to do that because we already have 3D Gaussians. We do not have to take care about empty space. So that is different. But basically strategies Both of them are based on rendering equation. So this was summary. We first project Gaussian to screen space and sort them by depth order, and then accumulate contribution of Gaussian based on depth order, and then there's no neural network. That is summary. And then let's see details about the projection first. So as I said, there are 5 parameters in Gaussian, right? 3D mean, scale, rotation, opacity, and color. But there are 5 features, right? This is mu. So we project mean. This is mean. We can project mean position of Gaussian from world coordinate system to image coordinate system using camera parameter. That is what we learned in so far, right? Using camera extrinsic and intrinsic. And the projected Gaussian form an ellipsoid footprint in screen space determined by its covariance and depth. Covariance, it includes scale and rotation. So that the footprint of ellipsoid might depending on the covariance. If scale is large, then the projected Gaussian might take many pixels. If there is some specific rotation, then the projected ellipsoid should be depend on the rotation. And the depth, if depth is small, then of course the projected size of the Gaussian is very huge. Depth is large, then the projected Gaussian might take small pixels, right? Because that is of a perspective projection. So this is projection, that's what we learned so far. And then rasterization. I think we studied rasterization for mesh, right? We heard rasterization in mesh. So in mesh, rasterization was projecting, let's say this is screen space. And then projecting triangle face to the screen space. That is rasterization. Some stage that we need to do first in advance for the rendering. That is actually rasterization. For each pixel, for the 3D Gaussian, this is mesh. For the Gaussian, for each pixel, contribution from overlapping Gaussians are accumulated using alpha blending based on opacity. So this is show alpha blending. So we have opacity, right? In here we have opacity. Opacity means density. So if density is low, then the projected Gaussian have very transparent. So that we need to consider project the opacity of each Gaussian when mixing projected Gaussians, because there can be many Gaussians, and for some pixels like this pixel might take more than one Gaussians, right? This pixel might be affected by this blue Gaussian, and at the same time it is affected by this green Gaussian. So we need to mix them, mix blue and green Gaussians. How can we blend them? So we have opacity, right? We have opacity. So we project Gaussians, and then each Gaussian has opacity at depth order. And based on this kind of depth order opacity, we do alpha blending. In the screen space, that is important. We do this in screen space. In case of nerve here, we did this kind of a little bit similar to alpha blending in 3D space, right? We cast a ray, and there's a ray marching, and then we accumulate transmittancy by adding this estimated density, multiplying density, right? In 3D space. But Gaussian splatting, we do that in 2D space. We do alpha blending in 2D space, projected screen space. So we project all the Gaussian in the image space, and then we consider depth ordering. We blend all the projected Gaussians because some pixels might be included from more than one Gaussians. And Gaussians are rendered in front to back order. That is definitely correct, right? In depth sorted. To ensure correct transparency and compositing. And this rasterization step is implemented with custom CUDA code. CUDA is some platform of NVIDIA GPU. Typical Python script, it is not very good for this kind of operations. actually there should be many for loop in this kind of CUDA in this kind of alpha blending and rasterization for loop. As you might know, for loop is not good for Python script, right? It is, because each pixel can have different number of Gaussians, so that it is not very easy to make them a tensor shape operation. If we can make tensor shape operation, then Python is good, but script-based language is good, like Python, but each pixel might have different number of Gaussians, so that it is not very easy to incorporating this kind of tensor-based parallel computation in this Gaussian rasterization, so that the authors implemented this rasterization step with custom CUDA code. CUDA code is C++, so that it can be used for loop efficiently. So very fast, very fast. And finally, we can get images. Define a color as computed as a weighted average of Gaussian colors, modulate by their transparency. Once we alpha blend it, then we have, that is about weighted averaging actually. We weight average Gaussian colors, modulate by transparency. We will cover this mathematically later. That is based on random equation. And as you can see, accumulated image, these are rendered images using 3D Gaussian splatting. The accumulated image forms a high quality rendering that naturally capture soft edges, transparency, and depth continuity. And this rendering is real time. That is also very surprising thing actually. This kind of photorealism and real time rendering, that makes 3D Gaussian splatting very strong. And these days, many people are interested in 3D Gaussian splatting to represent 3D scene or 3D object. Another good thing is that it can be obtained from a casual input, like a video captured with a mobile phone. It does not require, of course, we can use multi-view capture system, then it is definitely good. But although we have a single mobile phone, that's good. This video is from single mobile phone. Once we optimize Gaussian splatting with a video taken with our single mobile phone, then we can render images with any viewpoint. And this is the optimization process pipeline of 3D Gaussian splatting. So the first one, initialization. Here, initialization. We learn structure from motion, right? Structure from motion. Structure from motion, the input is a video, multiple images, right? Input images or a video. Then output is sparse point and camera parameter, right? So assuming we have a video, and then we can run structure from motion, and then we can get sparse 3D points and then camera parameter, that becomes initialization of 3D Gaussian splatting. As I said, it's very similar to MVS, multi-view stereo. Multi-view stereo, to do multi-view stereo, we required a sparse 3D points and camera parameter, right? So for the 3D Gaussian splatting, we also need a sparse point cloud and camera parameter. Of course, there are many follow works that does not require structure from motion, that does not require any initialization, random initialization, but original one that requires structure from motion initialization. And as you can see here, these are randomly initialized 3D Gaussian splatting, and this is initialized from structure from motion. As you can see, randomly initialized 3D Gaussian splatting gives quite good results, not very bad. Once we zoom it, then we can see definite difference. There is many unrecognizable artifact when we randomly initialize 3D points and camera parameter. Then if we initialize point and camera parameter from structure from motion, then it gives quite good result. So the original 3D Gaussian splatting requires initialization from structure from motion. And it starts from isotropic Gaussian. So do you know isotropic Gaussian? Isotropic Gaussian means so isotropic means so same direction. I mean, so there can be like this kind of different shapes, but isotropic means restricting degree of freedom to 1, just the sphere-shaped Gaussian. This one, degree of freedom is 3, but this one, degree of freedom is 1. So always have the same, I mean, scale it becomes 1D, scale 1D. So x, y, z are scale with the same number. Rotation, there is no rotation because each Gaussian is considered as a sphere. So we start with isotropic Gaussian because the anisotropic Gaussian is of course expressive, but anisotropic Gaussian, it needs more data to optimize, so that at the first stage the optimization is not very mature. So they start with isotropic Gaussian. Degree of freedom is 1. Just consider Gaussian as a sphere, not the ellipsoid. And then once we optimize in some level, then we can shift to anisotropic Gaussian. So the optimization start with isotropic Gaussian, and initialization is from structure from motion. And then this one initialization, and then we learn projection, right? Initialization, we initialize point in the world coordinate system, and then we can project Gaussians to the screen space using camera parameter, right? That is also from structure from motion. And then differential rasterization, we learned this, right? We project all the Gaussian to screen space and then do alpha blending in screen space, considering depth order and opacity of each Gaussian. We rasterize, and then we learn that, I mean, once we alpha blend projected Gaussian, then we can get images. That is what we get from theoretic Gaussian. And then for optimization, we need gradient, right? Then, like NERV, we use only captured images for the supervision. We do not use 3D geometry supervision. We do only use image loss. For example, L1 distance between rendered image and captured image. There is no 3D level supervision. That makes this pipeline very practical. We can get images, right? We take a video, then we have many images, and then we just use images as supervision target. Ground truth is only image. There is no 3D geometry supervision. That makes our algorithm very practical because preparing 3D geometry ground truth is not very easy. So this one makes very practical. And actually, there's also one limitation of 3D Gaussian splatting. Not very easy to incorporate 3D geometry loss in 3D Gaussian splatting pipeline. So in some case, we can prepare very accurate 3D mesh ground truths using 100 cameras, using multi-view stereo, very good state-of-the-art multi-view stereo algorithm. We get mesh, very detailed, good quality mesh ground truths. But supervising 3D Gaussian splatting with such kind of mesh is not very trivial actually, because we cannot define similarity between 3D Gaussian and mesh. How can we define similarity between 3D Gaussian and mesh? That is not very trivial. Because 3D Gaussian splatting, as I said, it does not have explicit surface, so that it is not very easy to define differentiable similarity function between 3D Gaussian splatting and mesh. If we can invent it, then we can just use it for 3D supervision. But so far, there's no good such kind of 3D loss function. So instead, people often render depth or normal maps to multiple viewpoints and then compute loss on them if we have ground truth depth and normal maps. I mean, it is not necessary. This is not necessary. Not necessary. Image loss is good. If we only have image, then we can use images. But if we have 3D geometry ground truths, or if we have some depth or normal map ground truths, then we can use such kind of geometry supervision by rendering depth or normal maps from 3D Gaussian splatting. Because we cannot measure similarity between 3D Gaussian and mesh in differentiable way, in particular, so that it is not very easy to incorporate 3D supervision. So instead, people incorporate multi-view 2D supervision to supervise 3D Gaussian with 3D geometry. But in casual setting, if we do not have 3D ground truths, we only have images, then that's all. If we can use images in this, we can compute L1 distance between rendered and captured images. And actually, but the image loss is very tricky, as you can see from this video. You might expect this one is outside of this scene, but the image loss is very tricky, especially if we have a limited number of images. Then image can cheat geometry, so that because image, it does not provide any 3D geometry information. It only provides color information, right? So that only relying on image loss, like 3D Gaussian splatting or NERF, it might fall in some bad local minima. So that is the reason why we need multiple images. Let's say we do not have 3D ground truths, then we need multiple images to address this kind of ambiguities, because images only provide a textures. It does not have any geometry information, right? If we optimize 3D Gaussian splatting with first few seconds of this video, then we can't guarantee anything about these pixels, right? So multiple images, including a single video or geometry ground truths, are necessary to optimize NERF or 3D Gaussian splatting or anything. And this is optimization, and adaptive density control is introduced optimization. And this one shows the comparison if this kind of adaptive density control is not introduced. As you can see here, rendering quality is quite bad, right? As you can see, there are many blurred regions. And here you can see detail is missing. So why this happened? This one is from very huge Gaussian. If Gaussian has huge scale, then, each Gaussian has single color, right? Each Gaussian has single color, but but if a certain Gaussian has huge scale, then it might produce this kind of single color, but huge blurry region. So typical reason of this kind of blurry stuff in 3D Gaussian splatting is too big scale of Gaussian. So that the authors try to address this kind of artifact by introducing adaptive density control. If we have enough number of observation, if we have like a 1 hour video capture of this scene, then maybe as we have enough number of data so that this kind of artifact might not happen. But if we limit the training video like a 1 minute or 30 seconds, then we do not have enough observation so that there can be some artifact in some regions that do not have enough number of observation, so that we need to introduce regularizer. This kind of thing is kind of regularizer, tries to regularize 3D GS using, given limited number of observation. And here, no clone. This one is clone split. So split is this one, clone is this one. No clone, then majority pixel looks reasonable, but you can see the detail of bicycle is missing compared to the ground truth one, or no, fully optimized one. And actually this kind of densify is necessary because initial structure for motion points are too sparse. We learned that structure for motion only provides 3D points for matched point, right? But the matched point, it does not provide, it is not for all pixels. There can be very few pixels matched between different images. So that initial structure for motion points are too sparse, so that it is not enough for photorealistic rendering. So that we need to densify them. We need to make them dense. So there are two things, clone and split, as we learned in this slide. Clone is for Gaussian with large gradients. We split Gaussian, simply copy and paste to make new Gaussian. This one. So if we clone, there are some details, like we slightly change the position of Gaussian according to their gradient direction, but basically it tries to just make a copy of this one into two different Gaussians. So they tries to make the number of Gaussian bigger and bigger. The large gradient means, to minimize image loss, it needs to change much, right? Then that means it is not converged. It is not converged yet. So we need something, so that we select some Gaussian with large gradient, because such Gaussians are not converged, so that we need something to make it converge, so that we split Gaussian with large gradient. The threshold is predefined hyperparameter. We simply copy and paste. We slightly move Gaussian, but basically copy and paste. Scale is same, rotation the same, all the things the same. For example, let's say the black region is the target region, but if we try to optimize this Gaussian without cloning, then this Gaussian might go to this direction, this direction, this direction. It might have very big gradient to minimize image loss function. It might just oscillate in this black region, so that for those Gaussian with large gradient, we clone this Gaussian to the two different Gaussians, so they tries to make the number of points larger. And then this one, split for Gaussian with large scale and gradient. Here there's no scale, but the large scale and large gradient. We split Gaussian with smaller scales, like this one. This one is, to minimize image loss, it needs to do something. For example, if this black line is target region, then to fit into this black region, the Gaussian should do something, but so that it make the scale very huge, but still the image loss. The image loss is quite big, so the gradient is still big. In this case, we have a hyperparameter for the scale threshold and the hyperparameter for gradient threshold, and then we simply, this is just cloning, means scale rotation is the same, as you can see, the same, but then we split this big Gaussian with huge scale to some smaller scale, as you can see. Gaussian has smaller scale, right, compared to this one, smaller scale. So some Gaussians with large gradient, we just make them, we clone them. Some Gaussian with huge scale, at the same time huge gradient, and then we can split them to fit into target region, right? And also we remove Gaussians whose opacity is smaller than threshold. There can be some abundant Gaussians whose opacity is too small, so that they marginally affect the rendering quality. Then we can just simply remove them, because they do nothing about the rendering quality. Opacity is small, then according to rendering equation, then if opacity is small, then it does nothing. So then we can just simply remove them. So that we can prevent too many Gaussians. If there are many Gaussians, then rendering becomes slow. It takes too much memory, so that we simply remove some Gaussians whose opacity is smaller than threshold. And let's go back to NERF and compare the NERF and 3D Gaussian splatting. This is rendering equation in NERF, right? We learned this. Of course, there were integral, but we can, as we do ray marching in discrete space, so that we can simply change integral to sigma. And that is the rendering equation in NERF. There's a T is a transmittancy, Ci is a estimated density. No, alpha is this one. Ci is color, right? Ci is color. And this one is estimated density. And this one is color pixel. We simply accumulate transmittancy, density and color and transmittancy, where transmittancy is the accumulated density. And this is really Gaussian splatting. This is color, and this is color each point, each Gaussian is a color. And alpha is the opacity, and this is transmittancy. Just accumulated opacity becomes transmittancy. And so you can see these are quite similar. This one is NERF, left one is NERF, and right one is 3D Gaussian splatting. Both of them get color of a pixel by multiplying transmittancy, density, and color, where transmittancy is the accumulated density. This is accumulated density. This is transmittancy, right? So, the detail might be a little bit different, but basically their philosophy is almost the same, because the reason is that both are based on same rendering equation. Same rendering equation, right? So that is the reason why we have very similar mathematic representation. But actual implementation is very different. As we learn, nerve, we need to cast a ray. Cast a ray is the same. 3D Gaussian splatting, we cast a ray. But the difference is that nerve, we need to do ray marching. This is I. We do ray marching, and then we evaluate all the point along the ray. And then evaluating means we pass all the point to the neural network to get density and color value of all point along the ray, right? With adaptive or fixed interval in the ray marching, right? So that makes really slow. That is the volumetric rendering. But 3D Gaussian splatting, so that is the reason why we call nerve as implicit function based one. All the point, we need to evaluate them based on learned function, and along the ray, all point needs to be evaluated. But explicit one, we already have 3D Gaussians. We do not have to take care about some space without Gaussian. We only need to consider 3D Gaussian points, so that so for the 3D Gaussian, we do not have to keep ray marching and keep checking the density and color of all points along the ray. We do not have to do that. As we learn, we project all Gaussian to the screen space using camera intrinsic and extrinsic parameter, and then just do alpha blending in screen space. So the mathematic representation is almost the same, but how to implement is very different. Ray is nerve combination of ray marching and learned function. 3D Gaussian splatting, Gaussian projection, and then alpha blending, right? So that Gaussian splatting, we do not have to take care about all points along the ray, and then each point, we do not have to pass them to neural network. That's two things makes rendering very fast. By checking all points along the ray, and then skipping neural network forward, we make Gaussian splatting rendering very fast, about 100 frames per second maybe, very fast, less than 5 frames per second. It's quite interesting, right? Mathematically, they look almost the same. How to implement them and basic philosophy is very different. Of course, Gaussian splatting is not universal solution for any cases. There can be many cases where 3D Gaussian splatting fails, but nerve do good job. But in many cases, actually, 3D Gaussian splatting is doing better than nerve. Mathematically, very similar, but actual implementation and philosophy is very different. And this shows, we learned the adaptive density control, right? If there's no density control, as you can see, there are many artifacts right here, many artifacts. As you can see here, there are many artifacts. Then this full, you can see, very close to captured images. So we can change camera in this optimized 3D Gaussian splatting. We can change orientation. We can change position of camera, so that in the final project, I recommend you just look around all the Gaussian. You can just move camera below this floor, below the plane, right? You can just camera inside of some object. You can put camera in any position, any orientation, so that you can see what can we get from this such kind of weird camera positions, weird camera orientation, and then we can composite some object in the 3D Gaussian. And there are many viewers because they support real-time rendering. We can see rendered images rendered in real time. And these are just the experimental result of 3D Gaussian splatting. It just did good job on majority of metrics, as you can see, over 100 frames per sec. Here, training time is 48 hours. Can you imagine 48 hours for a single scene? Very slow, right? Instant NGP is what we saw in previous class, the last slide. It takes only 7.5 minutes, right? Very fast. To make nerve very efficient, but rendering speed is very slow. Training time is very, very fast. Once we train it, we need to render some new images. But the rendering speed is 9 frames per sec. The rendering image over 100 frames per sec. Even with this huge gap in training time and rendering speed, the PSNR SSIM about the rendering quality, image quality. Image quality is very good, although there is huge gap in efficiency. And even with early 5-minute stop, it gives comparable result. 5 minutes rendering, because in 5 minutes, the number of Gaussian is not very big, because density, other to density densification is not done in enough number of iterations, so the number of Gaussian is not very big, so that the rendering speed is a little bit faster than the fully optimized one. But the quantitative evaluation, image quality, rendering quality is very good. Even we only train it in 5 minutes. And that is the reason why I make the 3D Gaussian splatting final project. If we make a NERF final project, then we cannot do that, because maybe you do not have high-end GPU, right? With your laptop, maybe it takes more than 48 hours. So we cannot do about NERF project. For the 3D Gaussian splatting, I think you can. You have laptop or some good level of desktop, I think you can. With this 30-minute optimization or up to 1 hour optimization, that might be reasonable, I think. As you can see, many detail missing. As you can see here, Gaussian splatting gives quite good result. The texture very blurry, right? Very blurry. Detail are missing. Limitation is that, so densification, as I said, is based on heuristically designed handcrafted one. We have threshold of scale, threshold of gradient. These are just empirically found, and these are the handcrafted one. That might be not optimal for all settings, right? It might be not optimal for all situations. And popping artifact is very important. So when we order Gaussians, when we order projected Gaussians in depth order, we consider depth of Gaussian. That makes sense, right? That makes sense, but the problem is that each Gaussian is not point. Each Gaussian has some size, right? So, depth of each point might be reflected in the depth order rendering, or we have size of Gaussian. So in some case, let's say this is ray, this is camera, and so let me draw again. This is eye, and this is ray, and there are some Gaussian and some Gaussian, like this one. So this is P1, P2. So depth of P1 is smaller than P2, right? You can see this depth point. Let's just look at the mean of the Gaussian. Mean of the Gaussian, depth of P1 is smaller than depth of P2, right? But the problem is that each Gaussian has size and rotation, so that there can be some pixels where P2 has smaller depths in, like this region, right? Can you see? Because each Gaussian is not a point. Each Gaussian has scale and rotation, so that mean-based depth sorting actually is not optimal. It does not take size and rotation of Gaussian into account, so that there can be so depth ordering might not be correct. Depth order might be wrong, so that they might make some popping artifact. And size of the 3D Gaussian actually is quite big. we have like 3 to 6 millions of Gaussian. That might take about up to 700 megabytes. Is very big compared to alternatives like 50 megabyte or 10 megabytes. So kind of memory inefficient. Of course, these days people try to make it very efficient, but original one is suffer from memory inefficient. The rendering time is very good. Okay, any questions about this one? 3D Gaussian splatting? All is clear? So we learned many 3D representations, right? Mesh, point cloud, voxel, nerf, and 3D Gaussian splatting. Those 5 things are the commonly used representation in these days. And I recommend you get familiar with all the representation and what is the strength, what is weakness of each representation. And in some situation, what would be good option, good representation in some situations. Each representation has strength and weakness, and actually that makes this kind of 3D vision, 3D graphics very interesting. For images, we only have square shape image, right? Video, you have only square shape video. But 3D stuff, we can choose some representation based on your preference, and then based on some situation, there can be many options, and each representation has strengths and weakness, and that makes, quite diverse approaches. Okay, if you have another question, then let's check the attendance and finish.